Hello, welcome to my YouTube channel. Today I'm going to introduce two mathematical models of COVID-19 spread. First model is the simplest one, and its name is SIR. Here each letter SIR stands for the susceptible, the infected, and the recovered. This model was already introduced by many YouTube channels. One from Numphile channel, which inspired me the most, and the other one is Tom's YouTube channel. I'll leave those links below and please go check out. Second model is the extended version of it by including more variables, and its name is SEAIHR. Don't get freaked out yet, we'll get to this more later in this video. I implemented Lyra's version here, and for those who are curious more details of this model, please go to his GitHub website after watching this video. Before we start, let me tell you that the one that you can see on the screen is the second model. Without further ado, let's get started with the simplest one. In this simplest model, for total population N, we only care three types of people that are the susceptible, the infected, and the recovered. Here, we are interested in how the number of people for each kind changes over time. Imagine that we have an estimate of infection rate and recovery rate. We assume that these are constant. What I mean by constant is that it does not change over time. We all know that this is not realistic, but this is just for the sake of simplicity. Now let's see how we can model the dynamics of those three types of people based on our common sense. Considering that the infection happens from the infected to the susceptible, the changes of the susceptible is decreasing with infection rate multiplied by the number of contact between the infected and susceptible, and then divided by n. This is the equation 1. For changes of the infected, it is more straightforward. We already know that the number of infected will increase with infection rate and decrease with recovery rate, as you can see in the equation 2. Now the third equation is just saying that the number of people recovered changes with the recovery rate multiplied by the number of infected, which makes total sense. Now it's time to see how the susceptible, the infected, and the recovered will change over time respectively. In this simulation, we assume that the total population N equals to 1. We also assume that at time 0, there is 10% of infected people. So the starting infected rate is 0.1. If we change this value, we can see that the value at time 0 changes. So let's put it back to 0.1. In this graph, the pink line represents the susceptible, red line represents the infected, blue line represents the recovered. We'll see how the graph changes as we change the value of infection rate. For the sanity check, let's set this transmission rate to 0, which means there will be no more additional infection. Therefore, the initial infected people recovered at the end and no more virus. So we can see that the blue line approaches back to the original point of the red line at time 0. Once we start to increase the transmission rate here, which is same as the infection rate, we can see that the red line increases rapidly in the early time period. Let's stop. And if we set a transmission rate as 10 times higher than the recovery rate, which is 3, we can see that the most of the people got infected at almost day 3. This time, if we decrease the transmission rate, we can flatten the red curve. Now it is time to talk about second model, which is SEAIHR model. This model is a little bit more complicated than the first one because of the additional 3 more variables. Each letter of SIR has the same meaning as the above. The letter E represents the exposed, A represents the asymptomatic who does not have any symptom even when they are infected. Because of this asymptomatic patient, we saw in the first video that the reported cases are not exactly the same as the actual cases. The letter H represents the hospitalized or the quarantine out of the total infected. Since we have more variables, we need more parameters to explain the dynamics. Incubation rate in the second line is equal to 1 divided by the days before the symptoms. In the previous videos, we assumed that the incubation period is 5 days, which is equivalent to say incubation rate is 0.2. We differentiate the recovery rate for two types of patients, one with symptom and one without symptom. It is reasonable to set it differently now that we can expect the asymptomatic patient will recover faster than the one with symptom. We also need a parameter of the ratio between the symptomatic and asymptomatic cases. When fraction is 0.8, this means that 80% are patient with symptom and the rest 20% are the patient without symptom. Lastly, we need a parameter of days in hospital. Now, using all those variables and parameters, we can model the dynamics of the susceptible, the exposed, asymptomatic, the infected, the hospitalized, and the recovered. And I'm quite sure that once I start to explain these crazy looking differential equations, many of you will just stop watching the video. So I'll skip to the simulation, but I highly recommend you to pause the video and look it carefully. If you are still with me, you deserve to see this animation right now. In this graph, the pink line represents the susceptible, the red line represents the infected, and the blue line represents the recovered. Orange line represents the exposed, the green line represents the hospitalized, the gray line represents the asymptomatic patient. This simulation is under the parameter set of 10 days in hospital, 15 days of infection, 80% of symptom fraction, 20% of infection start ratio, 5 days of incubation, and 0.01 quarantine rate, and 0.554 infection rate. For the sanity check, let's start this animation. For the sanity check, let's make this value extremely low to 0 and to 1. To me, it seems alright. And let's see how effective the quarantine policy is. It's better to go with this. We can see that the higher quarantine rate successfully flattens the red curve. Alright, that's all I prepared for today's video. Thank you for watching. If you find this video useful, please press the like button and don't forget to leave a comment if you have any question. In the description section below, I'll leave all the information about references and the link where you can go and play with this simulation by tweaking the parameters. Thank you again and stay safe.